Welcome to the Organic Chemistry 2 final exam review. Um, we'll go ahead and just jump right into this. Let's see, there is already a question over, did you call it Claisen addition? Or what were you? Yeah, please feel free to use your microphone if you wish. If you don't want to use your microphone, that's completely fine too. I understand. Claisen condensation is something from the alpha carbon chemistry chapter where you have the removal of hydrogen to form on the alpha carbon to form the negative nucleophile, but this is not that. This is something from the earlier chapter with alcohols and. Oh, okay, I see. So, well, this is basically a Diels-Alder reaction. It's a Diels-Alder reaction of a type, um, where you have the diene and the dienophile. So this is the reaction that you're interested in?
Yes, that's one of them. I just realized I did. Yeah, that's a Diels-Alder.
Yeah. Rather than your typical Diels-Alder reaction, this one, since you're doing it with a triple bond, essentially what you have to understand is the mechanism here is that these pi electrons right here are going to go ahead and they're going to form a single bond. And that's going to break this triple bond, or break one of the bonds anyway, and cause those electrons to come down here and form a sigma bond, which is going to break the double bond, when I say break the double bond, but it's really just going to move those pi electrons down here. And so you end up with a double bond that forms here, and that was these electrons here that moved. And you also still have you have two of the three bonds from the triple bond that are still present. Now, in this case, because this is a trigonal planar structure, you're going to end up having there's not going to be any wedges or dashes. You would have wedge or dash concerns in terms of say if the dienophile was trans and you had the diene here, you'd end up getting a trans addition product. The double bond here. And because it can really actually come from either end, you can from the top or the bottom, the diene can add to the dienophile, either from the top or the bottom. And because of that, you can really end up getting this, or it's an enantiomer. See, I believe you just get a racemic mixture in that case. So there's going to be an open review. I was not able to get a practice final exam from the professor, from Dr. Gilchrist. And not honestly because she wasn't willing, but honestly because I was just too busy to reach out to her, in all fairness. But I'm happy to go over any questions you might have from any of the tests, any of the practice tests on our website, or any of the tests that you have that you've already taken, because I know she does give those tests back to you. Likewise, any questions from the book or any other resources you have are also welcome. So just let me know what you would like to go over.
If the dienophile has like a carbonyl on it, isn't there like a preferred orientation that it has to be to add?
In this case, I don't I don't think so. I mean, okay, so depending on the complexity of the molecule, there are certain steric considerations that need to be considered, or that need to be taken into account. Obviously, you want to try to do something that will give you a continuation of some resonance delocalization, because that will be it will improve the stability of the molecule. But other than that, uh, I don't I don't necessarily think that there's any sort of special considerations that need to be kept in mind with regards to that particular thing. I mean, yeah, you're not going to use. I mean, the dienophile should not be a carbonyl. This should be a carbon-carbon double bond, or a carbon-carbon triple bond. But as far so the carbonyl should be retained. But other than that, there's not a whole lot, I think.
Could you show how to prep an epoxide real quick?
Sure. So there's how to prepare an epoxide. So there's two main ways in which you will um, you'll form an epoxide. Um, the easier slash more common way that I've seen is using a peroxy acid on any sort of alkene. So you could have like R C double bond C, and then and actually I'll just put R2 and R1 because these don't have to be identical. And then all you have to do, and of course the H here, this really could be either cis or trans, but basically um, this is going to be a syn addition. So you're going to have something adding either on top or on bottom. And so you're going to have those considerations in mind. But if you react this with some sort of a peroxy acid, and some of the most common that you've seen are MCPDA, CPDA, which is metachloroperoxybenzoic acid. And sometimes it'll just simply be written alternatively as something like this. It'll be like R C double bond O O O H, or sometimes even more simply as R C O 3 H. Any of those are basically shorthand for some sort of a peroxy acid. And what that's going to give you, it's going to give you the epoxide. So this, well, actually, that second bond is gone. And instead of that, you're going to end up having the epoxy group. And of course, these carbons will still have the hydrogens attached to them. And I'll show you how to look at how to deal with the stereochemistry of the epoxides in just a second. But I want to show you the other method as well. The other method would be if you take an alkene and you do a two-step process. You can basically do step one, which is halohydrin formation of Br2 in water. That's going to give you an OH on one side and a Br on the other. And it's going to be an anti-addition, not a syn addition. Then you follow that up with NaOH. And what the NaOH is going to do is it's going to provide a base in order to rip off the hydrogen from that from the halohydrin. So essentially the intermediate you get here, the halohydrin intermediate, it's going to look something like this. You're going to have have a bromine here, and the bromine easily might be on the other one because the bromine is going to add basically to the is going to add to the less highly substituted carbon, whatever that is, and the hydroxy group or the OH is going to add to the more highly substituted carbon based on the mechanism from the halohydrin reaction. But essentially what happens is that hydrogen on the oxygen is going to get, the hydrogen on the OH is going to get ripped off by the NaOH. And so that's going to end up giving you an O minus down here. And this reaction, of course, is in equilibrium because technically speaking, if we wanted to be entirely honest with you, the OH group, the hydrogen on the OH is actually less acidic than water. So that NaOH is not going to completely deprotonate. It's just going to deprotonate a little bit. It's going to go back and forth in equilibrium because it's not necessarily favored here. But when it does become deprotonated, you're going to undergo what's an intramolecular SN2 reaction, where basically this oxygen's electrons are going to come in from behind and kick out the bromine, and the bromine is going to leave, and you're going to end up with the epoxide. So the halohydrin followed by NaOH or some other base, that's going to typically give you this halohydrin. So let me draw what this would look like. It'd basically be the same thing. And because the mechanism is a bit different, because you do end up getting um, anti-addition versus syn addition. There's a different stereochemical configuration in your final product here. But those are, so that's your, those are the two ways you can get an epoxide. Let's go, yeah, go ahead.
Oh, I was just going to say, depending on whether the starting alkene is cis or trans to each other determines whether the epoxide branches there will be cis or trans as well.
Yeah, it would be original. So, so let's go over the stereochemistry of an example here. I think it's more complex than simply cis or trans. So let's go ahead and take a look at that if that's cool. Everybody has what they want from the screen? Is it okay if I clear it? I'm going to assume that silence means consent in this case.
Yeah, I think so.
All right, so let's take, for example, I'm going to show you a very specific stereochemical example. Let's say, for example, I have something like this. Here's a CH3 up here. And let's say I have a CH, CH3, CH3. Kind of an isopropyl group coming off that. And over here I have a hydrogen, and I have a CH3 here. So in a case like this, were I to react this with metachloroperoxybenzoic acid, or MCPDA, I can either add from the top or the bottom. Because remember, this is planar. This is a flat molecule. There's no wedges or dashes. If I add from the top, so that the oxygen plants itself on top of that, it's going to push those groups down. So what we're going to want to do is we're going to rotate this molecule such that this and this are going to go back away from us, and this are going to come out towards us. Does that make sense? So this and this go back away from us, and this come out towards us.
Okay.
So picture that in your mind. Okay, and then the oxygen's going to plant itself right on top. That's going to mean that, so here is your epoxide. Now the wedge group is going to be the ones that were on bottom have now come out towards us, right? And that's going to give us CH3 here, CH3 here, and the ones going away from us, it's the CH3 back here. And then likewise, on the other side, I have a CH3 that's going to be coming towards us. And then I have a H group that's going back away. Can you see how that worked? I just tilted the molecule backwards and then planted the OH on top of it. Now here's the thing though. I could have done it the other way. I could have had the hydrogen and the CH3 group on top tilt towards us and the other two groups go back. And so I would get the one that I've drawn here plus its enantiomer. Okay? So what is the stereochemistry of this particular molecule? Well, if I'm looking at this, if I look at the carbon on the left-hand side, it's chiral, and so is the one on the right. And there's 4 different groups bonded to each one. So this is my number 1 priority because it's the oxygen. If I go down into the group in front here, this is carbon bonded to 2 other carbons. Here's a carbon bonded to an oxygen and a carbon. So this one is actually going to be higher priority. This would be 2. And just as a point of reference, I'm looking at this particular carbon to try to indicate its designation as R or S. And then from the last 2, it's pretty simple. This is going to be 3. And the lowest priority group here is going to be 4. So it's going to be this one. Now, fortunately, the lowest priority group is in the back. And since the lowest priority group is in the back, I don't have to worry about flipping the configuration. I can just follow the arrows here. So I'm going to start with 1, 2, 3. That is clockwise. So that's going to be an R configuration. It's an R configuration for this one. For the other one, and I'll use orange. For the other one here, my number 1 priority group is once again going to be the oxygen. Number 2 is going to be this carbon over here. Number 3 is going to be the CH3. And the hydrogen is going to be number 4, lowest priority group. I don't care about the lowest priority group. Fortunately, it is in back, so I don't have to worry about flipping any configuration. It is in back. So I will just do the rotation. And it looks like 1, 2, 3. This is counterclockwise, so this is going to be S. So I am going to get an RS and it's an enantiomer. Now these are not identical on both sides. These are actually asymmetric. So the RS and the SR are not going to be the same. Strictly speaking, were I to name this, I could count from the side that's closest to the epoxy group. So this would be number 1. 1, 2, 3, 4, 5. So this would be so 1, 2, 3, 4, 5. There's a methyl group on carbon 4, and there's a methyl group on carbon 3. So it would be 3,4 dimethyl, 2,3 epoxy pentane. And of course, that would indicate the 2s3r. But its enantiomer would also be present. Notice that what I cannot get is an RR or an SS. If I wanted to get the RR or SS for this, I would have to use the alternate method of making this, which would be the Br2 in water, followed by NaOH. And that would give me the RR and the SS. Does that make sense?
Yes, thank you so much.
Yeah, no problem. I know those stereochemical considerations can get pretty darn complicated. So I just wanted to show that in detail. There are some tips or there are some little shortcuts and tricks and things like that that sometimes can be used like just memorization type stuff. But I've always preferred to look at it spatially because I found that to be more reliable in the long run. Otherwise, you start messing up some of the tricks you can use with one with some of the tricks you can't use with one. All right. What other questions can I have? What other question can I help you with? A spectroscopy question. Absolutely. I actually have some good spectroscopy questions. Let me see. I'm going to pull up a spectroscopy question from a practice problem set I have on the website. It requires you to use all of the different spectroscopy tools at your disposal to find the identity of a compound. Well, you tell me. I'll show you a couple different ones, and you tell me which one you'd like to do. Because admittedly, we want to pick something that would actually be appropriate to what your professor would be likely to ask. So here we go. So there's this question here, which is kind of interesting. It says, H&MR spectra of 4 isomeric alcohols, each with the formula C9H12O, are shown in figure 13.48. So this is 1 alcohol, 2 alcohols, 3 alcohols, 4 alcohols. And so you have to use the H&MR to figure out what the alcohol is, the structure of the alcohol given the C9H12O. Now, the other type of question would be interesting to do would be something like, here we go, 1346. Figure 1354 presents an IR, H&MR, CNMR, and mass spectra for a particular compound. What is it? So it's like, you don't get anything. This is like if you were actually in the lab and you had to do all the different spectra and use it to come up with a formula for a particular compound. So which one would you like to do? You want to do the harder one? Okay, cool. So let's take a look at this one, because this is a really cool problem, and it really gives you a chance to look at all the different spectroscopy issues that you could face. I'm actually going to go ahead and, you know what? I think I'm going to go ahead and download this and post it in our thing so I can pull it up and you can zoom it in as needed. We do that. That'll be fun. Feel like your definition of fun is rather strange. I'm like, yeah. Yes, it is fun. It's like, I don't know. I like problem solving type stuff. Like it's like putting together a puzzle, figuring things out. It makes you feel smart when you're done, at least, which has some merit. There we go. Sharing this with you now. Boom. Okay. Let's zoom this in. All right. So for the top part, oh, this is the same type of thing. So this works. We'll do this one, and then if you want, we can do the other one. So for this one, I'm looking at this, and it says a compound has the mass, IR, and H&MR structure presented. So the first thing is you'll notice that in the mass spectra, so that's what this is. This is the mass spectra. the mass spectra is really useful for giving us the molecular weight. That would be this. So our molecular weight is 134. Now, another thing that would probably be a good idea is for us to look and see if there's any signs of functional groups that we can pick up from the IR. So I'm looking at the IR, and one of the things I always want to do is I want to see if there's any peaks beyond 3,000. So here is 3,000. Do I have a signal past 3,000? What do you think? Actually, I do. You have to understand that the peak, this really needs to be nothing. It really needs to be nothing past 3,000 to not count. But if you look at this, if you look at that piece right there, there definitely is some carryover that's coming into the 3,100 area. And keep in mind, especially with aromatics, there are not very strong signals in the 3,100, 3,050, 3,100 range. It does extend out here, but it's not going to be a terribly strong signal. So there at the very least, could be an aromatic peak here. Another thing I can do to kind of check and be like, okay, well, if there is an aromatic, then we should see a few signals around 1,500, 1,450, 1,550, something like that. We should see a few C double bond C peaks. And if I look over here, yeah, actually we kind of do. Here's a 14, like a 1450. It's kind of a double-edged one, and then you got this 1,500 one. So this definitely could be, at least it could be, maybe not necessarily, but it could be an aromatic peak. Let's go down to our H&MR and see if we can confirm it. If we look at the H&MR, I see, okay, yeah, we have something between 7 and 8. When the hydrogens are in between 7 and 8, this is a very strong signal. There's a very strong signal that there is definitely an aromatic here. Definitely an aromatic here because CHs between 7 and 8 are really going to show up right there. Now, if I look back up here at our mass spectra, are there any signs of a chlorine or a bromine in this particular IR, or in this particular mass spectra? Any chlorines or bromines here?
Do we take into account those two little bars to the right of 134?
Those two little bars to the right are what are referred to as M+1 and M+2 peaks. You have to remember that there is about 1% of carbon ions. 1% of carbon ions tend to be C13s.
Right.
So that's going to give you an extra. Plus, I mean, you also have a very small amount of deuterium, but 1% of carbon ions is going to tend to be C13. Well, if we consider the fact that this probably has somewhere in the neighborhood of 10 carbon atoms, maybe not 10, but somewhere in the neighborhood maybe of 10, it turns out, and this is a really interesting calculation to do, because it's not what you would expect. If there's a 1% chance across 10 carbons, it's not simply 10%. What you have to do to figure out what is the probability of having something that's a little bit more. So it'd be 0.99, which is the probability of having of the first carbon atom being a C13, and then I have to multiply that times 0.99 for the second carbon atom, and then I have to multiply that by 0.99 for the third. And so basically, you keep on doing that, you end up with 0.99 to the 9th power, or 0.99 to the 10th power if it's going to be 10 carbons. And Just out of curiosity, what do you get if you take 0.99 and you raise it to the 10th power? I can tell you what I got.
Yes, please.
0.9,
Skills are not working.
0.99, that's good. 0.99 raised to the 10th power is about 0.904. So you actually start to get, so that means that for at least, so the probability that you're not going to have, the probability that you're not going to have a single carbon-13 atom in a particular molecule is 90%, which means that 10% are going to have at least one carbon-13. And so that means that's why you see these two peaks here, because the two tiny peaks here, one of these has one carbon-13, the other one has two carbon-13s. This one is noticeable, this one is barely noticeable. But you can see it actually ends up at that point being a significant amount. So that's just the M+1, M+2 peak. But the molecular ion peak is really what's going to help us to determine what the chemical formula of this is. I do not see any signs of oxygens or nitrogens here. And when I asked you about bromine or chlorine, here's the thing. Bromine and chlorine are really interesting because bromine, its two isotopes are roughly equivalent. Bromine 79 is about 50%. Bromine 81 is about 50%. So if you had a bromine in the molecular ion peak, it would show up like this. It's basically two peaks that are two away from each other that are identical height. Chlorine, on the other hand, is interesting. And I'm going to change that to green because chlorine is typically thought of as being green. Is it? Well, actually, I don't know if I chose green or yellow. I'm colorblind. Oh well, who cares? So, chlorine 35 has about 75%. Okay. Chlorine 37 is about 25%. So you end up getting 1/3 to 2/3 ratio here, and it's a very noticeable and consistent pattern, 1/3 to 2/3. So when you see the 1/3 to 2/3 where the shorter one is always the higher one, that's a sign that you have chlorine. If you have two peaks that are identical in height, that's going to be a bromine, if these are your molecular ion peaks. And you don't see that pattern in any of the mass spectra peaks, either the base peak, which would be like the largest peak, this is your base peak, or the molecular ion peak, which is your highest molecular weight peak. So the lack of the 3-to-1 or the 1-to-1 peaks is going to be no chlorine, no bromine. I don't see any signs in the IR spectra of an oxygen. I see no signs of a nitrogen. Nitrogen would show up over here. Oxygen would, if it was a carbonyl, it would show up as a big, deep, long spike right about 1700, right about there. If it was a single bond oxygen, you would notice some fairly deep, noticeable peaks at about either 1100 or 1300. They'd be about twice as long as this. It'd be at least down to here, and you're not seeing anything there. That whole region from about 10 to 1400 is completely and conspicuously absent. So no signs of oxygens, no signs of nitrogens. So this is just a hydrocarbon. And if I want to determine what this chemical formula is for the hydrocarbon, here's what I want to do. I'm going to take the molecular ion peak weight, which is the 134, and I'm going to divide it by 12. Let's see what I get. Okay. What does that give me? 134 divided by 12.
That's about 11.
Yeah.
11.166.
So the most, yeah, so 11.16. So the most number of carbons that this could possibly have would be 11. Now, if I take 11 times 12, 11 times 12 is, 11 times 12, let's think about this, is 132. So 132 would mean there's only 2 left for a hydrogen. So C11H2, does that seem like it could be a reasonable formula? Especially not if I go down to the HNMR, right? HNMR clearly shows that I have 14 hydrogens. This is where you have to use all your spectra together. HNMR clearly shows I have 14 hydrogens, so this is completely out. So I'll drop one carbon. Let's say I have one less carbon. If I had one less carbon, if I had C10, well, 10 times 12 is 120, right? So
Right.
10 times 12 is 120. If I subtract 120 from 134, what do I get?
14.
I get 14, which means I would have, and since hydrogens only weigh 1, that means I'd have 14 hydrogens. And that seems to be appropriate to what the HNMR is showing me below, because it says I have 4, 4, and 6. That's a total of 14 hydrogens. Okay, so now I'm good. This actually does match. This makes sense with what I have down in the HNMR here. Okay, so from there I have to figure out what is the number of degrees of unsaturation. And for that I can ask myself, well, a normal 10-carbon hydrocarbon, if it was saturated, would have how many hydrogens?
22.
If it was, 22. HN, or I mean, CnH2n plus 2, so that'd be 22. So how many hydrogens are missing here? 8. And if you take that amount of hydrogens that are missing and divide it by 2, that's going to give you the degrees of unsaturation. So exactly, 4 degrees of unsaturation. And a degree of unsaturation can either be a double bond, or it can be a ring, or any, it could be 4 double bonds, 4 rings, or any combination of the two. Now, whenever you have 4 degrees of unsaturation, you should be highly suspicious of what?
A ring.
Of an aromatic ring. An aromatic ring is exactly 4 degrees of unsaturation. And honestly, if we look at the other spectra, we can see there's signs of an aromatic ring in the IR, and there's definite signs of the aromatic ring in the HNMR. So we definitely have an aromatic ring. I'm going to actually draw that case here. So we have the chemical formula C10H14. We have an aromatic ring that compensates for 6 of those carbons and apparently 4 of those hydrogens. Since it says that I have 4 aromatic rings, or 4 aromatic hydrogens, this is going to be a di-substituted benzene ring. So now I have to look at what it shows me here in the HNMR. And I see 6 hydrogens that are showing up as a triplet signal. This is showing this as a triplet signal. 6 hydrogens in a triplet is going to be, well, what? I can't have 6 hydrogens on a single carbon, right?
Right.
Why not? Why can't I?
Carbon can't bond that many times.
Yeah, exactly. And so that means that it's going to have to be some other pair. Now, what does the triplet tell you?
Is that there are 2 neighboring hydrogens?
Yeah, there's 2 there's 2 hydrogens on an adjacent carbon. So that means that I have a C with 2 hydrogens next to it. Now, if that's the case, how many hydrogens do I probably have in that red signal or pink signal? How many hydrogens are actually on a carbon making up that signal. If it's not 6, it's probably what? 3. Yep, probably 3. Whoops, sorry. Hydrogen. And can we confirm this? Well, let's look at the other signal. If I look at the signal for the blue, that's a quartet. That tells me that that signal has how many hydrogens on an adjacent carbon? 3. Yeah, n+1 rule, right? So it looks like these two signals are meant to go together, that CH3 next to CH2. So it looks like, and since that's a 4, I'm not going to have 4 carbons if I also have adjacent, I'm not going to have 4 hydrogens on a single carbon if I have adjacent carbons, which I clearly do because of the signal splitting. So this is probably a 2 and a 2. So that tells me that it looks like since there's 4 of these hydrogens, the blue hydrogens, that means I probably have 2 CH2-CH3 groups. Because I have 2 CH3 groups giving me a total of 6 here, and I have 2 CH2 groups giving me a total of 4 here. Now I have one other piece of information here that makes it clear to me what I have. Because if I was just looking at the pieces here, I could be like, okay, well, I can have a CH, I have two ethyl groups. I can have a CH2CH3 here, and I could have one ortho. I could have one, I could have the 2 of them ortho to each other. I could have the 2 of them meta to each other, or I could have the 2 of them para to each other. How do I decide if it's ortho, meta, or para? I'll give you a hint. The key factor here is the singlet. The benzene ring that's a singlet.
Would it be para given the distance between the chemical shift?
Mm-hmm. Yeah, it's the singlet. The only way you get a singlet here is when identical hydrogens do not split one another. Identical hydrogens do not split one another. It's one of the weird things about H&MR. So the only way these hydrogens would be identical such that they would not split is if the 2 groups are para to each other. And so let's draw what that would look like. So if I have a CH2CH3 here, CH2CH3 here, I have 2 identical groups opposite to one another, and then I have these 3 hydrogens that are coming out of the or 4 hydrogens coming out of the benzene ring. Well, normally they would be split by each other and would give you a doublet. But the problem is they're identical because they have the exact same chemical configuration. If you look at the line of symmetry here, this has 2 lines of symmetry. There's one here and there's one here. The vertical one is not as easy to see. But those 2 lines of symmetry make each of those hydrogens literally identical. If the top group was different than the bottom group, you'd end up with 2 doublets, 2 sets of doublets. But in this case, you only have a singlet, which means all 4 are identical. What do you think? Do you think you could do a problem like that if you were pressed to it?
This exact one, sure.
um, yeah, I mean, admittedly, we took a long time on this problem. Uh, if you want to work on another one on your own, I'd recommend checking out the next one. This is the one that I originally showed you, and this gives you a CNMR, NMR, and IR and a mass spectra. And I'd recommend giving that one a shot. But I don't want to take up too much time on one topic if you have other questions. So let me know. So what would you like to look at next? I'm happy to cover anything that you want to cover. So even if it's the same exact thing, even if it's doing another one of these NMR ones. But um, what else would you like to look at?
Could we touch up on radical bromination?
Absolutely. Although I don't know if you would do radical bromination per se. I'm trying to think. Trying to think of class this one. If we did HBr, I'm trying to. If
Yeah, that's what I was thinking of, sorry.
yeah, no problem.
The
So
1214 adduct.
yeah, exactly. So let's take a look at that. That's actually a good question. So in a case like this, you have like HBr. I actually had a really good question, a test question that I would give tutors that were trying to be OChem tutors back when I was a managing tutor at this online site. And it was like, which one of the following is not a potential product of the following reaction? And I gave some sort of ridiculous diene with like the, and then they had to like, there was 4 possible correct products and only 1 incorrect product, so they really had to know how to do the mechanism. Um, but basically, here's what you have to understand. First of all, it's a hydrogen is always going to add hydrogen is always going to add to the position that's going to give you the most stable. That's going to give you the most stable uh, carbocation. So if now hydrogen could add to 2 possible positions here, and you say 2, that doesn't make sense. Why would it be 2? Well, it's because of this. If hydrogen has to add, if hydrogen is not going to add to the position that prevents resonance. So you're not going to get hydrogen, adding here. Because if it added here, that's locked. That double bond can no longer resonate. This is not going to happen. Even though it would give you a tertiary carbocation. So that means that hydrogen has no choice but to add to one of the other positions. So it has to add to the positions that will allow for resonance. So it can add to this position, and if it does, it'll give you this carbocation, which is secondary. Not too bad. It can also add to this position, which will give you a carbocation here, which is secondary. Once again, not too bad. I need to add in the double bonds. I might actually keep the double bonds in black just to, you know, make sure they stand out. Okay, cool. So if I look at the resonance, since both of these would give you a secondary carbocation, both of these are possible addition products. Okay. Um, and then of course we have resonance. So in the case of resonance, I can have the double bond shift over to here, and that would put the positive charge here on the primary position. Okay? And this, of course, means that the hydrogen is the one that added here. If I shift on the other one, I get the hydrogen still had added over here. If the double bond shifts over to where the positive charge is, you now have the carbocation here. So here's the deal. Which one of these two which one of these two resonance forms is going to be the major, which one of these is going to give you the major product? The major products, I should say. The major products.
I want to say the one on the bottom right.
Well, I mean, you have to include both.
Oh, okay.
Yeah, you have to include both of them because these are part of the same resonance form. The actual structure is actually a hybrid between these two. But yeah, so these are the two different locations where the hydrogen could have added. And this one is these two resonance forms are going to be the one that gives you the two major products, the kinetic product and the thermodynamic product. Okay, so the kinetic product is going to be the one that forms more easily, and the thermodynamic product is going to be the one that is going to be less reversible. It's also going to be the one that has the more highly substituted alkene. Because a more substituted alkene, remember, is more stable, right? So if I look at the bottom one, if the hydrogen were to add, or rather if the bromine were to add at the carbocation there, we would get the following product. Oops. We would get this. And the double bond would be here. H would add here. And I'd have a bromine add here. Does that make sense?
Yes.
And then if I were to have the other one, the bromine add to the other position, okay. Your hydrogen added here, and your bromine adds here. And the double bond is over here. Which one of these is more stable? Yeah, the first one. Why? So here's your more stable one. That's your more stable. It's tri-substituted. Very good. This is a tri-substituted alkene. Which is less stable. So that means the other ones are less stable, right? So if the less stable one is down here, the thermodynamic product is going to have to be which one? The top or the bottom? The top, yep. The more stable one is your thermodynamic product. Now, why would the bottom one form more quickly? Why would the bottom one form more quickly?
Is it because of the carbocation there?
Yes, look at the location of the carbocation. The carbocation is tertiary, right? So it's this one has the bottom one has a lower activation energy because the positive charge is on the tertiary position. So it's much more likely for a bromine to come in there when because the positive charge is in a more stable tertiary position. However, if you look at the top, the um, the tertiary it's in a secondary position, so that's not as favored. But here's the thing that we have to recognize about this particular reaction: this is reversible. It's reversible because that bromine that just added to that tertiary carbocation could just as easily leave, couldn't it? Because bromine is a good leaving group. It requires a little bit of energy to leave, but it is a reversible product. It is a reversible. So if you want the kinetic product, you would need to carry the reaction out at low temperatures. So this would be, the bottom one would be the major product at low temperatures. The top one would be the major product at higher temperatures. And the reason is because if there's higher temperature, then since the reaction is reversible, the higher temperature means there's more energy. It makes it easier for the bottom reaction to reverse so that it can switch over to the top one. And once it's in that more stable form, it'll tend to stay there. So even though you might get initially the kinetic product forming, it reverses so quickly, and it ends up so the product that you finally get is going to be the more stable, the thermodynamic product, if you have enough temperature. But at low temperatures, it doesn't have enough energy to reverse itself, and it doesn't have enough energy to overcome the activation energy needed to add to that secondary carbocation position. So the top one would be the major product at higher temperatures. And high and low is somewhat relative. The low in this case would probably be about close to freezing, maybe a little bit lower depending for this particular reaction. And high temperatures it'd probably be sufficient to do like 30 degrees Celsius, which is, not that high. It's even like body temperature, maybe a little bit less. That would be considered high in this case. But anyway, does that make sense?
Yes, thank you.
Yeah, no problem. All right. What next? Thank you. And just as a side note, the key takeaway from this is whenever you're doing a reaction, an addition reaction of HBr with a diene like this, make sure that you put the carbocation in a position where it can resonate. If you, for example, the two positions that you could not add the hydrogen to would be this one. Can't add the hydrogen there because then the carbocation would be stuck at a primary position and it would not be able to resonate. And you can't put the hydrogen here because then it would be stuck at a tertiary position and it would not be able to resonate. And resonance really increases the stability of these carbocations substantially. So protonate the outer ends first of a diene, and that way the carbocation can resonate. All right. So what else can I help you with?
Could we see the mechanisms for how to make an imine and an enamine?
So an imine and an enamine?
Yes.
Yeah. I mean, there's different ways to pronounce it. Some people say imine, but imine and amine sound too similar, so I just say imine. So In this case, you're talking about the addition of um, the addition of uh, an amine to a ketone to get an enamine or an imine, um, or an aldehyde. You could also add this to an aldehyde, but basically, so let's say we take a standard ketone, and if we reacted this with um, let's say a primary amine, say CH3. I'll keep it relatively simple, even if it was even if it was a more complex amine, as long as it was a primary amine, one in which there was an NH2, and then the number of hydrogens attached to the nitrogen determines what you can do with it. As long as if there's two or more hydrogens attached to the nitrogen, then it'll form an imine. If there's only one hydrogen attached to the nitrogen, then it's going to be an enamine. And if there's no hydrogens attached to the nitrogen, then you're screwed. Just kidding. Now, then we have a problem. The reaction's not going to work real well. But let's go ahead and take a look at how this works. So, first thing that's going to happen here is that the tricky part about these reactions is you want it to take place at a certain pH that is somewhat, or at least potentially slightly acidic. I believe the acidity here is typically about a pH of 4 or 5. You don't want it to be so high, though, that it protonates all the amine irreversibly, and makes it impossible for these lone pair of electrons to actually be present so that it can act as a nucleophile. But essentially what happens here is that you have, and depending upon your textbook, this amine is actually a pretty good. Some textbooks will show this as coming in and attacking here first, and kicking that up to here. And you could, I mean, that works. But it may actually, it actually seems like, and that's what actually your textbook says. But there are some that seem to indicate that it might actually work better if there is a protonation of that carbonyl first. But that's going to be tricky to do. So usually what happens is it's not, because the necessity of having those lone pair of electrons on here, usually you're not going to actually have this be acidic enough. This is not going to typically be acidic enough to protonate that carbonyl before the nucleophile comes in and attacks. So the nucleophile, the nitrogen here, is going to come in and attack, and then you're going to get this. O minus. Now that's a very basic, that is a very basic negative charge on that oxygen. So that's going to get protonated pretty darn quickly. And of course, now that this nitrogen has 4 bonds to it, it's positively charged and therefore somewhat acidic. But there's going to essentially be enough weak acid around that, I'm actually just going to put this as an HA, but there's going to be enough weak acid around that this is going to get protonated pretty darn quick. Okay. Okay. So then, and this really is, technically speaking, I think all of these steps are actually reversible, or equilibrium steps. So then, although the protonation of that is not super reversible. So this is going to grab that, and then you're going to end up with this weakly acidic protonated carbanolamine. NH2, Actually, I should probably draw the hydrogen bonds because that bond is going to be deprotonated. Hydrogen, hydrogen, and CH3. Positive charge on that nitrogen. So you'll have that weak conjugate base come about, the A minus now. And maybe that'll just actually be another amine. It probably actually would just be the amine, the CH3NH2 would probably come in and deprotonate that. And so that's what would happen next. You have this coming in, grabbing that hydrogen, and taking that off there. So then you have this stable carbonylamine. Relatively stable anyway. So this is another reason, so this is a neutral compound. This is another reason why you end up wanting to have it is present in an acidic, or at least weakly acidic media, the pH of about, I think it's like 4 to 5, is because you need to protonate this alcohol group here. So there's another HA that was just reformed in the previous molecule. It's a bit, probably in all likelihood, this protonated amine. Because there's a little bit of acid that's been dumped in there, probably a little HCl. And this is going to come and it's going to attack and grab that hydrogen here. So it is important to recognize that there's a protein, that this is a weakly acidic solution, and that's why this can happen. Even though we don't get the protonation of the carbonyl because that requires too great of an acidity, you can get the protonation of this alcohol group here. And note that it is actually somewhat preferred for the amine on the bottom to get reprotonated. That's just going to take you back to the previous step, and that doesn't move you any further forward on the equilibrium. Whereas if you protonate the top, even though this is less likely, it still does happen that the alcohol gets protonated, and when that alcohol does get protonated, that allows for the next step in the reaction to take place, and I'll show you what that is. Once I have the OH2, this water is a good leaving group. And once water leaves, there's very little water present in the system, which is why equilibrium is going to favor this water leaving and pushing this process forward. So this nitrogen still has another hydrogen attached to it. Got to add it here, like that. And basically what happens is this water, which is positively charged, now since it's a good leaving group, it can be kicked out by the amine trying to stabilize the fact that it's basic by forming a double bond here. And when it forms that double bond here, that's going to kick out the water. And like I said, because there's so little water in the system, this ends up being, for the most part, technically speaking, it's reversible, but there's so little water in the system that equilibrium is going to not favor the reverse reaction. That's why I'm going to put those unequal equilibrium arrows there to indicate that that's not going to favor it since there's so little water in the system. So now I have the nitrogen. I'm going to actually draw the nitrogen on top now because the nitrogen is now double bonded and it has kicked out that water molecule, and it still has that hydrogen attached to it. It's positively charged because it used its lone pair of electrons to form that double bond. So now the next step is that A minus conjugate base, basically the amine, the CH3NH2, which is probably what that A is going to be representing here. That's going to just come in, and it's going to rip off that hydrogen and put those electrons back on that nitrogen. And there you go. You now have, try that again. Nitrogen, CH3. You have an imine. Does that make sense? Any questions on that?
I was able to follow through.
Cool. Now the only difference in the mechanism for an enamine is that in a case where you do not have that extra hydrogen on in a case where you don't have that extra hydrogen on the nitrogen here, for an enamine, what you would end up having to do is you'd see these two hydrogens here, and technically speaking there's also hydrogens here, right? But you would try to make the most stable enamine possible, and basically what would happen is the base, CH3NH2, the base would take one of those hydrogens away. It would form the double bond, like right there, and kick those electrons back up to the nitrogen. But that only happens in a case where the nitrogen does not have sufficient hydrogens to do so. Let's actually show you, let's show you a brief example. Let's say I pick up a slightly different structure. Let's say, for example, in Bizarro Land Universe, you have an alternate amine. Let's say that instead of the one that we had above, we had something like this. That our original amine was actually a dimethylamine, and so you had this water. Everything happened the exact same way up to this point where you had the protonation of the water, but the nitrogen here is positively charged. The nitrogen here has this lone pair of electrons, has two CH3s, and no hydrogens attached to it. Okay? In that case, you'd still have the nitrogen donating its double bond here and kicking out this water. But at this point, and you'd still have this being favored because there's so little water in the system. However, the nitrogen now doesn't have the option of being deprotonated because it has two CH3s on it. And so this is a positive charge and no way to get rid of anything right there to enable it to be neutral. And it really wants to be neutral. So what happens is one of these alpha hydrogens ends up getting ripped off by the A minus. So you got A minus comes down here. Amine comes down here, recognizes that nitrogen really would like a lone pair. So it comes down here and grabs one of these hydrogens, which forms a double bond here and kicks these electrons up to here. And once again, the only reason this happens is because there's no nitrogen, there's no hydrogen on the nitrogen to be protonated. So it has to take the hydrogen from somewhere else. And then you would end up getting double bond here, single bond up to the nitrogen, and then a CH3 here, CH3 here, and then you have a lone pair here. And this lone pair is not going to be anywhere near as basic as the lone pair on the amine. So this is actually pretty forward favored. This forward reaction is more favored than the reverse one. Doesn't really want to go back. So this is how you'd get the enamine. Cool?
Cool.
Okay. What else can I help you with? How are you with the aldol condensations and the aldol additions?
Trying to search in my mind for it.
Do you know what's meant by the condensation?
Isn't that where H2O leaves?
Yeah, H2O leaves and you get the double bond, the alpha beta unsaturated ketone or alpha beta unsaturated aldehyde. And do you know what the triggers are that would cause that condensation to happen at a higher and lower temperature?
I don't think so. Well, at least for me.
The more resonance you have, the lower the temperature that you need, the lower the amount of heat you need to trigger that condensation to happen. In some cases, it's really hard to get the aldol condensation or the aldol addition product isolated because the condensation is so favored. Let me show you a couple of contrasting examples real quick. Is it okay if I erase this thing?
It's good with me.
Okay. So for example, let's say if you had an let's say you had a ketone like this, and it underwent crossed aldol addition with benzaldehyde. So the only thing that you could have happen here is that this has to add to, this one has to add to this. This can't add to this because you can't rip off a hydrogen from this. There's no beta hydrogen. But if you do have this add to this, which one of these hydrogens would be more likely to be ripped off?
Would be that ketone?
You get two possible groups of hydrogens that could be taken off, right? You could have the alpha hydrogens on the right or the alpha hydrogens on the left. Any idea which would be more favored?
I can't quite remember.
That's okay. So in this case, it would be the and the base. In this case, the base. I think hydroxide would be sufficient, but I think hydroxide would be sufficient in this case. You could basically, no pun intended, grab this hydrogen. These electrons would come here and kick the electrons up to the oxygen. And that's going to basically, that's going to give you O minus here because it's much more stable to have the negative charge on the oxygen. And see, now this is a more highly substituted alkene, which is why this side would be favored. There are cases in which you'll get the less highly substituted alkene to be the one that is the preferred one, and that's usually in certain ring form reactions because it'll produce the more stable ring form, but like an intramolecular. But in this case, yeah, we'll use the inner one here. Now, what happens here is that this comes down here, and that causes these electrons to come and attack here. And that kicks these electrons up here. And with these Aldol condensation type reactions, one of the things that I always recommend to students is to keep track of everything that's going on, because there's a lot of crazy stuff going on here, especially if you have really complex ketones and it's not simple like this. This is a simpler one. Number or label, it doesn't have to be like specific numbers regarding to naming, but number and label your carbon, maybe. So 1, 2, 3, 4, 5. And so then when you go and you to your other side, you're like, okay, well now I know I have this benzene ring. I have carbon number 5 should be, well, it's going to be an O minus initially, but this is going to be protonated into an alcohol. I'll leave it as an O minus for now. And there's also a hydrogen. I don't really need to show that, but I will. Now, here's the thing. Technically, this, even though I've drawn it like this, you have to keep in mind that the resonance form does actually have the lone pair of electrons on carbon number 3. So this is carbon number 3. The lone pair of electrons that's going to attach, the carbon that's going to attach to carbon number 5 is carbon number 3. So carbon number 3 here is going to be the one that attaches to carbon number 5. This is 5. This is 3. So what else is attached to carbon number 3? Well, I see carbon number 4 and carbon number 2 attached to 3. So carbon number 4, actually, since it's only 2, so carbon number 4 I'll have go down, carbon number 2 I'll have go over here. So label that carbon number 4, carbon number 2. Now what's going to be present on carbon number 2? What's going to be attached to carbon number 2?
That oxygen with the negative charge?
Yeah. Well, no, actually it's a carbonyl, right?
Oh, right.
Because it reformed itself. So this is your carbonyl reformed. And then carbon number 2 is also attached to carbon number 1, right? Can you see how labeling those carbons can be helpful?
Yes, very helpful.
Yeah. So I always, that was actually, I mean, admittedly, the aldol condensation for me, sometimes it was really difficult to keep track of all the carbons, especially since my professor would give us like ridiculous things like, oh, I don't know, like this. It'd be like, and you know, like, something like this. And it's like, yeah. It's like, what the heck? Trying to keep track of everything that's going on there. It was a bit of a challenge. When it's adding to itself and then trying to like, okay, so what the heck, how am I going to keep track of everything? So labeling was the only thing that kept me sane, honestly. So yeah, at this point, of course, you have the there's water in the system if you have sodium hydroxide. So I'll just go ahead and have water, water, and that's going to go ahead and protonate this negatively charged um, oxygen. It'll give you the aldol product. So now this particular aldol product is particularly unstable. Why? Why is this particular aldol product especially unstable?
It's because there's no conjugation between the benzene ring and that alcohol anymore.
Yeah, or rather that there could be if it's eliminated.
Ah, okay.
Exactly. So these two hydrogens here, and this is in basic conditions. So you end up you have an OH minus here, and the OH minus, it really wants to, if I can just get rid of that alcohol and do the condensation here, I can actually make this a heck of a lot more stable and conjugate this all the way through. And if I do just rip off one of those hydrogens, I can form the double bond and kick off OH. Now, usually you don't think of OH as a good leaving group, but in basic conditions with an aldol condensation, especially where you get this conjugated system, yeah, it's definitely something that you want to do. The more conjugation throughout the thing, the more stable it is. And so in this case, you'll end up getting you actually would not have to add much heat, if any at all, to make this go from the aldol addition product to the aldol condensation product. Because now this is conjugated all the way through. Now, if you just had a standard, here I'm actually going to go ahead and delete this, but if you had a standard aldol addition with just like maybe that original item adding to itself, so let's say you had something like this. There we go. With this, while it would give you some conjugation to put that to eliminate that OH and put that double bond there. It's not it's only it's a small amount of resonance delocalization with two pi bonds, as opposed to this one you have the benzene, the other one you have the benzene ring. So here, if you put the double bond here, you just have a little bit of resonance delocalization. Yeah, that's good, stable, and everything like that. But you'd really have to add some heat. You really have to add some energy to push this into getting OH to leave and having a hydrogen being ripped off of that alpha carbon. So this one, however, you have the benzene ring and you have this carbonyl here, so that if you can just get rid of that OH group that was up here, you can get conjugation throughout the benzene ring and throughout the whole molecule, and that resonance is going to dramatically stabilize that product. So that's one of the reasons why with ones where you don't have a whole lot of resonance, you're going to have to add some heat to really push that into condensation, an aldol condensation. But with ones where there's a lot of resonance, then you won't actually need to push it very hard at all. A very minimal amount of heat or even no heat would be enough to get it to go. I hope that helps.
Yeah, thank you.
Okay. We got about 15 minutes left. Wow, time has really flown. Is there anything else that I can help you with? Anything that you haven't seen yet that you'd really maybe feel a little bit not as sure about I can help you out with? Thiols. Anything specifically about thiols? Yeah, I mean, there's not a whole lot that you need to do too much with thiols. The truth is, thiols are much more acidic than their alcohol counterparts. So if you ever have something like an RSH, something like that, if you put that in the presence of NaOH, sodium hydroxide, or some sort of strong base, you're going to pretty much convert this almost completely to the sulfide ion. And the sulfide ion is a really, really good nucleophile. The sulfide ion here is a really good nucleophile. So that can act as, it's not a terribly strong base, it's actually kind of a weak base, but it's a really good nucleophile, and it can be used in a lot of SN2 nucleophilic additions. So you can actually react this with, like, let's say, for example, if you have an alkyl bromide, something like this, in this case propyl bromide, then this can just very easily come in and attack. Well, whoops, I actually probably should have shown the attack from the other side, but yeah, it can come and attack from the back side, kick out the bromine, and you can get what's known as a sulfide. Or a thioester, rather, a thioether. So it'll be essentially 1, 2, 3, sulfur, R. So there's that. Another really interesting thing is you can actually have oxidation of thiols to form disulfides. And to do that, you end up having this with not simply NaOH, but also bromine. So it's an NaOH and bromine. And so what ends up happening is, first you get the deprotonation of the RS, because it's the RSH is pretty acidic. And then this can then attack the bromine. I'll draw an orange because actually bromine is kind of like a orange-brown color, the liquid. I know I always think of orange when I think of bromine. And so this negative charge here on the sulfur, it's a really good nucleophile, and bromine's a pretty good leaving group. Even when it's attached to itself elementally, you can have this sulfur come attack this bromine and kick out the other bromine. And then you get this brominated sulfide, which is really interesting. An RSBR. And the reason why this is particularly interesting is because bromine's a really good leaving group. So then at this point, if I have another RS minus from when I had the NaOH rip off the hydrogen on these RS guys, what happens is this acts as a nucleophile attacking the sulfur and kicking out the bromine, and you end up getting this interesting disulfide product. Disulfide bonds are actually one of the very important bonds that help to make up the tertiary structure of proteins. It basically holds two cysteine amino acids together. This is a little tie to biochemistry. But yeah, so you get RSSR. I'm not sure if there is another type of sulfide that you were wanting me to maybe another type of sulfide mechanism that you were wanting me to kind of go and take a look at, but you can also oxidize sulfides. You don't have to know the mechanism for this, but like for example, if you had a benzene ring and you had a sulfur here that was, let's say, attached to another methyl group, you could actually use periodate, sodium periodate, which is IO4, and that would actually convert this. That would actually convert this to a sulfoxide. I think that's what it's called, sulfoxide. The sulfur here is double bonded to an oxygen. So that's sodium periodate. If you had a similar thing, you could if you use H2O2, sodium peroxide, you would actually get something called a sulfone. And these are a little bit weird, but sulfones actually, because sulfur can have an expanded octet, unlike oxygen and carbon, you can actually end up getting a double bond O on top and a double bond O on bottom. And that, once again, I don't think you need to know the mechanism here. To be honest with you, I don't know what it is offhand, but that would be a sulfone comparatively. Another interesting factor with the thiols is they can be used as alkylating agents, and this is pretty interesting because if essentially sulfides, these sulfur esters or sulfur ethers can actually attack. Is it okay if I clear the board here? Y'all got this? Can I clear it? Yeah, and this certainly could come up on test because whenever there's a process that allows you to alkylate something, that's kind of important. But let's say, for example, whenever you have like a sulfide, which is basically a thioether, this can actually, if you have like, for example, if you have like a methyl bromide or some other like alkyl halide, this can come and actually attack. Yeah. And kick out the bromine here. And what that will do is it'll actually give you a positively charged, somewhat unstable tri-substituted sulfide here. And so you end up with, your R, CH3, or not CH3, sorry. R, sulfur, R, CH3 here. And there's one pair of electrons. And this is now positively charged. And the really interesting thing about this is that if you get a negatively charged nucleophile, that can actually come in and grab that alkyl group and kick off the sulfide. So what type of nucleophile would you need? That's a good question. Let's see. I'm trying to think of I guess you could. And there's an easier way to do hydroxy, to add a hydroxy group. But trying to think of another good nucleophile. But like for example, if you did have a hydroxy, because this would work, it is a nucleophile. But you're looking for some other strong nucleophile, you could actually have something like this. You could have the negatively charged hydroxy come in. It would actually attach to carbon because that would then kick out the sulfide and you get CH3OH. Now, why would you do that as opposed to just like reacting CH3Br with, you know, hydroxide? I don't know. Maybe there may be some cases in which that would be useful. But anyway, that's all I can think of with regards to sulfides and sulfoxides and all that kind of jazz. Um, if you can think of anything else that you want me to go over, that's all I can think of right now with regards to the sulfur group styles and sulfides and such. So I guess we're almost out of time, and I wish I could. I feel like we covered just a small part of the semester. I wish I could have more effectively covered more in that time, but yeah, this is it's kind of like drinking from a fire hose at this point, right?
Yeah.
But well, let me tell you this. I will be in the Science Learning Center for the rest of the day until 8 o'clock tonight. So if anybody has any questions on OChem or anything like that, please feel free to come by and come and check me out. We'll have organic chemistry tutors straight on until 8 o'clock tonight, and you'll probably end up with me. Sorry about that. And then we also have a ton of resources. Don't forget to check out some of the other resources that we do have. If you're needing a little bit of help or if you want some extra practice problems, I'm actually going to take a moment just to share with you and show you some of the cool things that we have available for you. So give me just 1 second, just to remind you of what we have in case you're not sure. So if you go to if you Google TCC SE Science, and you click on, once you've got to our website, the Google sites, you just click on Chemistry Web Resources, and then go ahead and scroll down to OChem 2. So there are some good concept reviews here, including spectroscopy peak list and spectroscopy guides. And so this is also some HNMR and IR spectroscopy analysis samples. So a student asked me to do a request and kind of like break down some of the IR peaks, what to look for, etc. And so I did that and helped to show how they come correspond with a particular structural formula. I also have some just like generic spectroscopy lists to show you the general. Here you see the CNMR numbers, and here these are the general ranges in which these substances peaks tend to form. You can see them. And I have some more stuff with like IR as well and NMR. And so it'll give you a good idea of where these things are relative to those wave numbers. Then the other thing is practice problems. We don't have answer keys for the practice problems for these, and admittedly, I've been actually working on the answer keys for the second set. I had to have a couple arenes and aromaticities, reactions of arenes, electrophilic and nucleophilic aromatic substitution. That's something that we did not go over in this review, but will be covered in the test. So if you want to go over aromaticity, there's some really good practice problems with answer key here. I was not allowed to post the answer keys for the Klein book. Some of the professors objected to that when I asked about that. So, but I do have some good practice problems here, and you can always bring in questions, or you can always bring some of these questions to me, and I'll go over the answers with you in the SE Science Learning Center tutoring room. Furthermore, there's also practice tests, which I do have answer keys for. Practice tests from Dr. Gilchrist. There's Dartmouth College ones, so not necessarily covering exactly the same thing, but the same types of things, but just maybe not in the same depth. But you'll see some useful things there. There's also MIT OpenCourseWare stuff, which is pretty useful as well. And there's also some answer keys. I actually have to finish the answer keys for some of these, but there's one on electrophilic aromatic substitution spectroscopy, and I have the full answer key here. So that one's a really good one to look at. And then last but not least, I have the video tutorial library. I have not completely finished this, but I have everything up to carboxylic acids and their derivatives. And I don't have this chapter completely done, but I have some really good stuff on properties of carboxylic acids, nomenclature, reactivity of their derivatives, and beginning some of these reactions like oxidation of the benzoic position, how to prepare basically carboxylic acids. And then of course there's everything before this. Everything before this should cover everything that you have in your textbook. So everything in your textbook is present here in a video form. If you just want to see somebody actually describe, if you're a visual learner and you want to see somebody describe as they write the different structures down. So anyway, I know that was a bit much, but just wanted to introduce you to some of those things that are available to you if you need them. And I hope that was helpful. Thank you so much for coming. Really appreciate having you guys here.